Hello everyone, welcome back to Mining of Massive Datasets. We're going to continue our discussion of the AdWords problem with a look at the balance algorithm. The balance algorithm is a way to deal with the problem of limited advertiser budgets in the context of the AdWords problem. To refresh your memory on what the AdWords problem is, we are given a set of bids by advertisers for search queries and a click-through rate for each advertiser query pair, and in addition, a budget for each advertiser. The budget could be for a day or a month or a year or some period like this. Let's just assume that it's a daily budget. Finally, there is a limit on the number of ads to be displayed with each search query. This limit could be 1 or 2 or 3. Now, we need to respond to each search query with a set of advertisers such that the size of the advertiser set is no larger than the limits of the number of ads per query. Each advertiser who we show has actually bid on the search query. And finally, if the ad is shown and somebody clicks on the ad, then the advertiser should have enough budget left over to pay for the ad when it's actually clicked upon. So we don't actually want to show ads from advertisers who don't have a budget to pay for the clicks if they do actually happen, because that's not a winning proposition for us. So the question is, how do we deal with this issue of limited advertiser budget, that we don't want to show or cannot show an ad from an advertiser whose budget has been exhausted? Now let's first study the problem in a simplified version. The simplified version that we're going to look at has only one ad shown for each query, and all advertisers have the same budget B. We're also going to assume that all ads are equally likely to be clicked and all have the same value of 1. Another way of thinking about this is that the expected revenue from each ad, which is a product of the click-through rate and the bid, is equal to 1. Now, the simplest algorithm is the greedy algorithm, which we've already looked at. And the greedy algorithm picks any advertiser who has bid 1 for a query when that query shows up. And it's easy to show that the competitive ratio of the greedy algorithm is actually a half. But here's a bad scenario for the greedy algorithm. Here there are two advertisers, A and B. And let's say A bids on query X, B bids on queries X and Y, and both have budgets of $4. Now the query stream that comes in is XXXX, YYYY. That's 4 X's followed by 4 Y's. Now when these queries come in, the greedy algorithm, when it sees the first X, notices that we have both A and B who are bid for query X. And let's say the greedy algorithm arbitrarily assigns query 1 to advertiser B. And then the second X comes in, and let's say the greedy algorithm assigns that to B as well, and so on. The greedy algorithm might, for instance, end up assigning all the first 4 X queries to advertiser B, none to advertiser A. As a result, when the first Y query comes in, B's budget of $4 is already exhausted, and therefore no ads can be shown for the Y queries. As a result, the greedy algorithm's revenue is only $4. Whereas the optimal allocation in this case, as it's easy to see, is to show A's ad for the first 4 queries and then B's ad for the next 4 queries. And that's the optimal choice, and the optimal algorithm has a revenue of $8, which is twice the greedy algorithm. And this is the worst case example that shows that the greedy algorithm can do half as well as the optimal algorithm. Now, it's actually quite easy and straightforward to prove that the greedy algorithm cannot do worse than this, and the competitive ratio of the greedy algorithm is exactly a half. And the proof of it is quite similar to the proof in the case of the online bipartite graph matching problem, which we covered in an earlier lecture, and I leave that to you as an exercise. The question is there an algorithm that has a competitive ratio of better than a half for this problem? And it turns out that there is, and it's a very simple algorithm called the balance algorithm. And the balance algorithm uses a very simple heuristic. For each query, it assigns that query to the advertiser with the largest unspent budget, or the largest balance, hence the name, the balance algorithm. If there is a tie, for example, if there's a query and there are 2 advertisers, each of whom have an equal balance, then the balance algorithm breaks ties arbitrarily, but in a deterministic manner. Let's look at how the balance algorithm deals with the example that we just saw. So here again is our example. There are 2 advertisers, A and B. A bids on query X and B bids on queries X and Y, and both have budgets of $4. Now, when the first query X comes in, the balance algorithm, both A and B are eligible to be shown for this query, and both have an equal balance of 4. And the balance algorithm has to break this trie arbitrarily. Let us say the balance algorithm assigns the first query to A. Now the second X comes in, and now notice that let's write down A's and B's balances right there. Notice now that A's balance is 3 and B's balance is 4 because $1 of A's budget is already spent when we showed the first ad. And so the algorithm assigns the second X to the advertiser with eligible advertiser with the largest balance, which is B in this case. And so that goes to B, and B's balance now becomes 3. Now, when the third X comes in, both advertisers are eligible, and once again, both balances are equal. The balance algorithm has to break the tie arbitrarily, and let's say it gives it to A. When the fourth X comes in, once again, it goes to B, since it has a larger balance. Now, when the first Y comes in, the only eligible advertiser is B. A has not bid for a query Y, and so the query has to go to B, and B's balance goes down to 1. And when the next Y comes in, it once again has to B, and B's balance goes down to 0. And when the last two Ys come in, there is no eligible advertiser, so we end up not assigning those queries to any advertiser, or in fact not showing any query for those searches. So as a result, the balance algorithm has a revenue of $6 because we show 6 ads in the balance algorithm. The optimal algorithm, as we recall, has a revenue of $8. And so the competitive ratio in this case is 6 by 8, which is 3/4, which is better than a half, right? So that's exactly what happens here. That's a balanced choice and the optimal choice, and the competitive ratio is 3/4. And in fact, it can be shown that for balance with 2 advertisers, the competitive ratio is in fact exactly 3/4. We can do no worse than a competitive ratio of 3/4 in this case. And the proof is quite simple but quite interesting, so I'll walk you through it. So let's analyze the 2 advertiser balance scenario. Let's consider a very simple scenario where there are 2 advertisers, A1 and A2, both with budget B. And let's assume that the optimal solution exhausts both advertisers' budget. In other words, the optimal solution has revenue to B because it allocates a B amount of budget from A1 and a B amount of budget from A2. Now, it must be the case that the balance algorithm exhausts at least one advertiser's budget. Because suppose the balance algorithm did not exhaust at least one advertiser's budget, then when a query comes in, both advertisers are eligible, and at least one of those advertisers can be shown for that query, and therefore it could do a bit better. So it must be the case that the balance algorithm must exhaust the budget of at least one advertiser. Now, assume without loss of generality that balance actually exhausts A2's budget, but doesn't exhaust A1's budget. Let's look at the simple visual to help us understand what's going on here. And let's say let's assume that these 2 rectangles represent sets of queries. In this case, the blue queries are the queries that were allocated to advertiser A1 in the optimal solution, and the green rectangle represents a set of queries that were assigned to advertiser A2 in the optimal solution. Remember that there are B queries of each kind, since we exhausted both A1's budget and A2's budget, and so there were a total of 2 B queries that were allocated by the optimal solution. Okay, and this is the optimal solution. Now let's look at what happens when we run the balance algorithm. When you run the balance algorithm won't assign queries in exactly the same way as the optimal solution. Let's say that some of the blue queries that were assigned to A1 in the optimal solution remain assigned to A1 in the balance solution, but some of the blue queries are instead assigned to A2 in the balance solution. And some of the green queries that were assigned to A2 remain assigned to A2, but some of the green queries that were originally assigned to A2 could not be assigned and are in fact left unassigned by the balance algorithm. Okay, and in fact the revenue of the balance algorithm is equal to B, which is the set of queries that are assigned to A2. Remember, since we exhausted A2's budget, plus Y, the set of queries that were assigned to A1. Right, so the optimal revenue in this case is 2B, since the optimal algorithm assigns B queries to A1 and B queries to A2, so its revenue is 2B. The balance revenue is B plus Y, since the balance algorithm assigns B queries to A2 and Y queries to A1 and leaves X queries unassigned. Okay. Now, what we're going to show is that we're going to show that Y is greater than or equal to B by 2. Why are we going to show that? Well, once we show that Y is greater than or equal to B by 2, then we know that the balance revenue is at least B plus B by 2, which is 3/4 of the optimal revenue. Okay. Let's consider two cases. Case 1 is when the balance algorithm assigns at least half or B by 2 queries of the blue queries to A1. Okay. So if the balance algorithm assigns at least B by 2 of blue queries to A1, then we know that the size of the blue bar is at least B by 2. And so Y is greater than or equal to B by 2, and we've shown Y is greater than or equal to B by 2, which is what we wanted to show in the first place. Now, the second case to consider is that the balance algorithm assigns less than B by 2 blue queries to A1, and therefore, since there are a total of B blue queries that are assigned, it must assign more than B by 2 blue queries to A2. Now, when more than B by 2 blue queries are assigned to A2, let's consider the last blue query, the query right here, the last blue query that was assigned to A2. Okay. When you look at the last blue query there that was assigned to A2, the balance algorithm, remember, both A1 and A2 are eligible and have bid on the blue queries. But the balance algorithm, and both at this point have unspent budget. But the balance algorithm decided to assign this blue query to A2. Remember the heuristic of the balance algorithm. The balance algorithm assigns the query to the advertiser with the larger unspent balance. So at this point, when the blue query was assigned to A2, it must be the case that A2's balance was larger than A1's balance. Okay. This is just another way of saying that at this point, the number of queries assigned to A1 must have been greater than the number of queries that were assigned to A2, since both started out with the same budget in the beginning. Now, we know that at least B blue queries have already been assigned to B by 2 blue queries have already been assigned to A2 at this point, right? And since we've said that the number of queries assigned to A1 at this point has to be greater than the number of queries that is assigned to A2 at this point, it must be the case that the number of queries assigned to A1 at this point, which is Y, is also greater than or equal to B by 2. And so we've shown that Y is greater than or equal to B by 2 in the second case as well. Now, since we've shown that Y is greater than or equal to B by 2, and we also know that the balance revenue is B plus Y, since Y is greater than or equal to B by 2, we know that the balance revenues is greater than or equal to 3B by 2, and therefore the ratio of the balance revenue to the optimal revenue is at least 3/4. Now, we've analyzed the simple case of balance with exactly 2 advertisers and shown that the competitive ratio is 2. But what happens if there are more than 2 advertisers? What happens if there are a large number of advertisers? In the case where there are a large number of advertisers, it can be shown that the competitive ratio of balance is given by this expression 1 minus 1 over E, where E is the base of the natural logarithms, 2.718, so on, and that is approximately 0.63. Notice that this competitive ratio 0.63 is strictly better than a half, which is the competitive ratio of the greedy algorithm. So the balance algorithm does much better than the greedy algorithm in terms of competitive ratio. Now, interestingly, although I won't be able to show this in this lecture, no online algorithm can actually do better than this competitive ratio of 1 minus 1 by e for the adverbs problem. But what I'm going to do instead is I'm going to show you the worst case example that gives us this competitive ratio of 1 minus 1 by e.